Okay, so this microphone is working, yes. So this morning what I wanted to do was just talk about hot stuff, finite temperature thermodynamics of the vinegar, to show you how this is done if you don't know it already. Then also I wanted to introduce everything coordinate beta ansatz and thermodynamic beta ansatz for spin chains. So a bit like yesterday, it's a completely insane plan. Nobody's ever taught all this material in 1 hour. So hopefully you've made use of the notes, and you will make use of the notes to kind of keep up and catch up. Did any of you look at the notes yesterday as compliments to the, okay, one person, that's great. 2, 3, oh, very good, very good. Okay, so maybe I can start by asking you whether you have questions about the last lecture. You know, there are things that you kind of bucked on and need to understand before we carry on, or can I just carry on straight? Any questions yet? No? Okay, well then let me assume that you've understood everything about coordinate beta ansatz for the linear, and I will just spend a little bit of time talking about equilibrium thermodynamics here. I will try to complete that within the first half hour at the most, so at least I can then spend the rest of the time on spin chains. Okay, so the beginnings of this lecture are all contained in chapter 5, which is really about t different than 0. Okay, so yesterday we've understood how to construct individual eigenstates. Now we're going to try to calculate at least our first physical properties. And like I said yesterday, it's very difficult to do anything with beta wave functions except recognize what their energies are and classify them, so we can do some at least equilibrium physics with them. So the main object to study, of course, when we do equilibrium thermodynamics is to look at the partition function z, which is going to be just the sum over all eigenstates, or the trace in Hilbert space, of e to the, and we're going to work in a grand canonical ensemble, so there's going to be a chemical potential mu, sorry, that's not a t, that's an n. Okay, divided by the temperature here, of course Boltzmann's constant to 1, etc., etc. So, provided we are able to calculate such an object as the partition function here, we are able to answer all questions about expectation values of things related to energies. So we can calculate specific heats, compressibilities, whatnot. So that's going to be the first object that we have here. Now, the question is how we realize this trace here. It's simply a summation over all possible eigenstates, but I've shown you yesterday that the eigenstates are cataloged one-to-one by choices of sets of quantum numbers. So provided you span through the whole set of sets of non-coincident quantum numbers, you will span your whole set of eigenstates. So really what we write this trace as is a summation over the particle number, which goes from 0 to infinity, and then a summation over these sets of quantum numbers, sets with cardinality n here, okay? Non-coincident sets here. So that's the object that we have here. Now, of course, we cannot calculate such an object exactly at, at all orders in particle number. We have to take the thermodynamic limit in order to obtain a controllable calculation here. So what we do is a bit like yesterday. We go to the thermodynamic limit, okay, and we introduce densities of occupied and unoccupied quantum numbers. Okay, so you remember we had this variable quantum number divided by L. So we had this, use variable xj, which was just a quantum number ij divided by L. This becomes a continuous variable. And essentially what we're going to do is we're going to visualize the real line of this quantum number variable as being made of little boxes containing a large number of quantum numbers, okay, but still having an interval delta x, which will go to 0 in the thermodynamic limit, L going to infinity. Okay, so what we do is that we separate the real line in boxes of width delta x, okay, where delta x is very much larger than 1 over L, but is very much smaller than 1. Okay? And then in these little boxes delta x, there will be a large number of occupied and unoccupied quantum numbers. So these are given to you in equations 5.2. So we define densities, you know, the row hole, and the row total, giving for you the density of occupied, empty, and total quantum numbers. Okay, so this is just like in equation 5.2. Okay. Row hole, and row total of occupied, empty, or total number of quantum numbers. Okay? So essentially in the thermodynamic limit, what we will do is do a functional integral over these distributions of quantum numbers rho. Okay? So the idea is that, let me maybe skip a few details. I mean, the details are, maybe I can explain them a little bit. Right? So you have your sets of quantum numbers. Say we have something like this. Okay, and then we define our boxes. Say this is going to be one of the boxes, this is going to be another one of the boxes, then this one, etc. The number of elements in the box goes to infinity. Maybe here it's a choice of regularization. You might put logarithmically log L or square root of L quantum numbers in there. It doesn't really matter when you take the limit. But essentially the conventions are such that, for example, in this interval delta xj here, there will be L rho of x delta xj occupied. There will be L rho hole of x, I'll call it xj, delta xj empty. Okay, and there will be L rho total, available quantum numbers. Now, the thing about the thermodynamic limit is that we pack together many, many states that are not distinguishable anymore under the thermodynamic limit. That is, we will associate or we will identify with one another states that correspond to each other modulo permutations of the positions of the occupied quantum numbers within the boxes. Okay? So that means essentially that we have a mapping of eigenstates to these functions, which is many to one. It's not one-to-one anymore. However, this does not matter provided we are not interested in asking questions about high-order 1 over L corrections or exponential something L corrections to what we will be calculating. Okay? So what will happen is that when we do the summation over eigenstates, we will do the functional integral, but include a fugacity in the term. Fugacity simply counting the number of states that we identify together, that are represented by these functions. Okay, so essentially in the notes you have a detailed description of this. What you have is that states are identified modulo in-box permutations. Okay, so we can start talking about the entropy of a state labeled by a function rho, a density function rho. This entropy is simply the number of permutations that we are allowed to make. Okay? And this is the famous form of the yang-yang entropy that you have in the notes in equations 5.4, 5.5, etc. Okay, so what it means is that the summation, so the important statement is that the summation over eigenstates in the thermodynamic limit becomes a functional integral over the density. So let me write it just like in the notes, d rho of x. Okay, but now there's counting of the states corresponding to the same densities rho of x. Okay, so this S of rho of x is an extensive quantity, which is known as the Yang-Yang entropy, because Yang and Yang introduced it in their first study of thermodynamics, finite temperature thermodynamics of integrable models. And it's written as follows, so you just add the integral dx, and then just by using Stirling's formula, so just counting the number of permutations that you have using Stirling's formula, you arrive at the form that is just rho plus rho whole, log of rho plus rho whole, minus rho log rho, minus rho whole log rho whole. Okay, so it's just like all entropy terms that you might have come across, you know, so Shannon entropy and whatnot, it's always of this form here. Okay, so you understand what I'm doing here? Is that clear? Okay, so now essentially we've managed a complete rewriting of our partition function calculation in terms of a single functional integral. Okay, so this is extremely advantageous because, as you will see, a simple saddle point evaluation will allow us to obtain a closed form expression for the kind of typical thermal state that you have in there. Okay, so now essentially our partition function, we can just rewrite directly in the thermodynamic limit as this functional integral Should I explain this better?
No, the initial action.
So let me just quickly go back. Let's see. Here, you see what you do is that you take, so you define your boxes. Okay, so let's define the boxes here, like this. And now I tell you that I'm not interested in the microscopic positioning of the occupied numbers within this box here. So here I have 4 available slots, which I have to fill with 3. So essentially I just get 4, choose 3 different terms that are different eigenstates, if you want, but these different eigenstates are not distinguished in the thermodynamic limit. We pack them up. So essentially you see you've got just the, when you take the limit of this becoming large, you can approximate this binomial coefficient with Stirling's formula, and you get it. Now you, yeah, is that clear? Okay. Yes?
How is the measure of integration is constructed, or it is not important in the thermodynamic limit?
So the measure of integration, actually, I construct carefully in the notes. So the important, let me just say it in words because it takes a bit of time to justify it properly. If you look at equation 5.8, you will see exactly what I mean by the functional integral measure. So actually in the literature you're going to find people just not giving you details of that. But this is really a completely well-defined functional integral in the sense of 5.8. What you do is that you have to realize that the densities in quantum number space, they obey a certain number of interesting properties, if you want. First of all, the quantum numbers are completely independent variables. If you modify the configuration of certain quantum numbers somewhere else, it does not affect in any way the statistical weight corresponding to the distribution of quantum numbers somewhere else. So therefore, the quantum numbers are the correct independent integration variables that you have. Okay? So that's the first property. The second property is that the densities in quantum number space are strictly bounded. They are strictly bounded between 0 and 1 in the thermodynamic limit. So therefore, the functional integral corresponds to an integral from 0 to 1 for each of these boxes that you define. Okay? So then, later on, we will change variables to the densities in rapidity space. if you try to define the functional integral in rapidity space, you have to implement all those constraints, those limits of integrals in here, which now become very complex because the density in rapidity space at lambda depends on the configuration of rho of lambda at other points in lambda, okay, because of the boundary of the integral, which varies. However, in the thermodynamic limit, this is not important. The only thing that it tells you is that if you would require me to calculate corrections in 1 over system size to arbitrary order, or maybe exponentially small corrections in system size to the functional integral, then I would need to implement these limitations here. Okay, so that's why in the existing literature, nobody talks about that at all, because it's not really important. But actually, if you are interested in finite size corrections, you do have to do that quite carefully. For example, these days, there are many arguments about transport in integrable models that depend very sensitively on the boundary conditions and how you modify them. So when you start doing those calculations, you have to ask yourself whether the integration measures don't include a term that you need to take into account in there. Okay? But in the notes, you will find the proper definition for the functional integral. Okay. Does that answer your question? Yeah. Anything else? Yes?
So the only approximation you need to take is the thermodynamic limit.
Yeah, so essentially, you see, I'm not making a specific choice of regularization, because I'm not telling you what my width of boxes is, okay? But you see, you can now choose it however you want. So I have my quantum number space, which is the whole real line. You know that at low temperatures, the rapidities are going to be concentrated around 0. So then you might say, okay, what I'm going to do in quantum number space is that I'll choose the delta x to be, say, I don't know, log L. Alright? So the number of quantum numbers you would have in there, you would say, let me scale it like log L, for example. Okay, or square root of L or something. And then you would do that everywhere. And then in the thermodynamic limit, of course, this becomes completely well defined in terms of rho of x, because you will expect rho of x to become a smooth functional. So if you want, if you require a very detailed calculation of the finite size corrections, then I will require you to specify the regularization scheme that you are using to go to the rho of x notation. Okay? But if you're just interested in the leading term, then you don't even need to specify it. You just say that, you will do something. I'm not sure I'm answering your question, but
yeah.
Okay. Okay, so that's how you kind of do it. Now, the nice thing is that our partition function takes the form of, functional integral, like you've seen very often. So you just have the entropy that appears here, and then of course for a given eigenstate, the eigenstate's energy is also going to be a functional of this rho, and the number of particles in the state is also a functional of rho. So the number of particles is just the integral of the density. Okay, so we obtain a functional integral over a single function describing the full thermodynamic limit of our partition function. Okay? So you see here, I'm still integrating over these densities in quantum number space, but remember the beta equations. The beta equations can be interpreted as a mapping between the real line space of quantum numbers to the real line space of rapidities. Okay? So I have as information rho of x, rho whole of x, rho total of x. Rho total of x is trivial because it's 1. Rho plus rho whole is equal to rho total. So in quantum number space, I just have this single functional integral here. Now if I rewrite this functional integral in rapidity space, I have to be a little bit more careful, because what I can do, so move to densities in rapidity space. Okay, so then my partition function in the thermodynamic limit will become a functional integral. Okay, but now I have to be a little bit careful because my entropy will take the same form if you want. So the entropy is still going to be the integral of rho plus rho whole, log rho plus rho whole, minus rho log rho minus rho whole. But now it's going to be in rapidity space. Okay? But rho and rho whole are non-trivially related to one another in rapidity space, unlike in quantum number space. So really what I have to do is do a functional integral over the rho of lambda, but also the rho whole of lambda, e to the s of rho whole. Okay, so now I'm being a bit cavalier with the notations. Here it's just the entropy in as a function of rho of lambda, again minus e minus mu n divided by t. But now I have a double functional integral, but of course these two densities are related by the continuum limit of the beta equations that we derived at the end of last time. Okay, so if you give me a certain density of holes here, I will have to solve for a density of rho. And you see that's where the complication shows up, because not every function rho of lambda is allowed. Okay? Because rho whole has to be limited by either 0 or rho total. Okay, so essentially the double functional integral that you have here is much more complicated to define. Okay, and has to be defined as simply a change of variables from this one, which is completely defined. So this functional integral here is a functional integral over these two functions modulo the imposition of the continuum limit of the beta equations. Okay? And you remember, so let me just rewrite it like in the notes. So rho plus rho whole is equal to 1 over 2 pi plus c star rho. Okay? But now it's okay. So this is completely well defined if you go back to the quantum number space definitions. Okay, now the form of this is like a usual functional integral that you have for many body systems, etc. The main characteristic is that, of course, it is amenable to a saddle point evaluation because everything in the exponent is extensive. It is proportional to system size. Therefore, I can just do a steepest descent evaluation of this. Okay, the entropy is extensive, energy and particle number. So particle number we take to be extensive as well because we want to work at finite density. So everything in the exponent is extensive, proportional to L. Okay? And therefore, in order to evaluate this functional integral, I can do an expansion based on the saddle point evaluation. Okay? So this is essentially the central idea of the thermodynamic beta ansatz. Okay, now the calculation for these things is given to you in chapter 5. So essentially, just a kind of useful notation here is that you just rewrite this as the functional integral of some Gibbs weight. So a g of rho, which is also, if you want an explicit function of rho whole, modulo the beta equations. Okay? So this Gibbs free energy is just the usual thing. You remember you just have the entropy and then the chemical potential and the free part of the energy. You have it in, I write it in equation. So C 5.14 in the notes. Okay? So in order to implement the saddle point evaluation of this, I just have to find the state which minimizes this Gibbs free energy functional. Okay? So what I do is that I just consider a variation of the densities of particles and of holes. I write down the equations for the variation of G under that. I also impose the link between the change of particle densities and hole densities coming from the constraint of the thermodynamic limit of the beta equations, okay? And then I obtain an equation for a row of lambda which describes a state lying at the saddle point of this functional integral weight. Yes? Okay? So that's the logic of the thermodynamic beta ansatz, if you want. There are exponentially many states in the Hilbert space. However, at finite temperature, there exists a pocket of states in Hilbert space which contributes all the same thing, because they all have, in the thermodynamic limit, the same limit value of the Gibbs free energy density. And then, of course, their number makes the whole calculation here. They all contribute the same thing, and that's what you see. I mean, you all know the saddle point logic, right? It's just an accumulation of states that give you the same thing, and then you can neglect the others. Okay? So this is the simple logic of the thermodynamic beta ansatz. Now, the implementation of these variations you find in the notes. Okay? So implementation of saddle point logic. So C notes, equations 515 up to really equation 525. Okay, so what this leads to in the end is, in terms of the new function epsilon of lambda, is by definition t log of rho whole of lambda divided by rho of lambda. Essentially what you get is a single equation for epsilon of lambda. Okay, so just see the logic. We have two free functional degrees of freedom, rho of lambda and rho whole of lambda. The beta equations give one relationship between these two functions. The condition of thermal equilibrium, that is the saddle point condition on the Gibbs free energy here, gives a second functional relation between the two. Therefore, there exists a unique solution here. You can show that the solution exists, actually. This is proven in the Yang and Yang paper. For the Bose gas, it's quite simple. So essentially what you obtain is that there's a single equation that can be solved to describe the thermodynamic equilibrium. And this equation is an equation for this epsilon of lambda. The equation looks like this. So you just have that this is lambda squared minus mu. And then minus c convolving t log of 1 plus e to the minus epsilon of lambda divided by t. Okay, so this you'd be entitled to call just a Yang-Yang equation. Okay, so again, this is our fundamental Cauchy kernel, just introducing the interaction dependence, if you want. And then you need to solve this equation for epsilon of lambda. If you find the equation for, or if you find the solution for epsilon of lambda, then you can calculate the Gibbs free energy. So the scaled one. So this one is going to be a function of the chemical potential and of temperature. And it's just the big Gibbs divided by system size here. So just the proper free energy density of your system. And then it's just equal to the integral d lambda over 2 pi with log of 1 plus e to the minus epsilon of lambda over t. Okay, with a factor of t in front. Yeah, so t minus. Okay, so if you want, when you look at this free energy density here, you are thinking of a system of free fermions with a dispersion relation epsilon of lambda. Okay, lambda is a bit like momentum, it's just quasi-momentum, it's not exactly momentum. But if you had a gas of free fermions with a one particle dispersion relation epsilon of k, you would write the free energy as just integral dk of log of 1 plus e to the minus epsilon of k divided by t. Because your fermions can be either, your fermionic modes can be either unoccupied or occupied with 1. If they're unoccupied, it gives you the 1. If they're occupied with 1, it gives you e to the minus epsilon over t. Okay? So, a beta ansatz solvable model, in a sense, you can always interpret in terms of a gas of free fermions. What are the free fermions? Well, they're essentially the objects that you would associate to your free quantum numbers. Okay? But of course, these excitations, they obey like Pauli exclusion principle, so they're fermion-like, but they're not coupled in any direct way to local fermion excitations and things like that. So this is just a kind of useful way of thinking about your Hilbert space, not your wave functions. Okay? Nonetheless, it is completely remarkable that the Gibbs free energy of such a system of interacting bosons takes the form of a free gas of fermions with a specified dispersion relation. Yes?
So if every model can be considered as free fermion, what distinguishes them between different models? What is the difference between these two? So
the dispersion relations are of course very different. So if you want, you have here so give me a certain value of the interaction parameter, certain value of the chemical potential, certain value of the temperature, and I will give you an epsilon of lambda. Okay? However, this epsilon of lambda is, if you want, a fictitious quantity, because of course you get the full Gibbs free energy density from this form here. However, it doesn't mean that your actual physical excitations have an energy dispersion relation corresponding to this function. Okay? What happens in integrable models is that excitations in the vicinity of the thermal equilibrium state, they have dispersion relations that are indeed given to you by these epsilons here. Okay? However, this only works if you create a thermodynamically zero density set of excitations over your state. Just imagine your ground state. You have a ground state with 1,000,000 particles. Then, to a very good approximation, if you create one particle hole, the energy is going to be the sum of the energy of the particle plus the energy of the hole. And the energy of the particle will be given essentially by the function epsilon. But then if you start doing it with 100 excitations, it's okay, it's fine. But if you do it with 500,000 excitations, then it doesn't work anymore because you have reorganized your state. So you're only entitled to essentially do zero entropy modifications around your states by keeping this logic here. If you do a non-zero entropy modification of your state, then you should start from scratch and redefine a new epsilon of lambda. Okay? So essentially what you have here is an epsilon of lambda which is set by finite temperatures. Of course, you could tell me actually, well, let me do something a bit bizarre with my gas. Let me say, put half the quantum numbers one way and half the quantum numbers the other way. Okay, and then consider finite temperatures around that. Say you add a kind of Mexican hat potential to your system, and you see what that gives you. You would be able to write a thermodynamic equilibrium equation also for such a system. It would take exactly the same form. The only difference would be, so the Gibbs free energy part here would take exactly the same form. The only difference would be that the epsilon itself would be given to you by a different driving term. It wouldn't be lambda squared minus mu anymore, but it might be lambda to the 4 minus 3 lambda squared minus mu. Okay? But there would still be an epsilon of lambda corresponding to that pseudo-equilibrium state. And the free energy would, again, be of the form integral log of 1 plus e to the minus epsilon. Okay, so if you want, all the physics is hidden in the epsilon, but the epsilons can take a whole variety of forms. Right? So in spin chains also, the epsilon shapes are going to be different depending on which state you consider. Yeah? But the fundamental aspect of beta ansatz solvable models is that all of them, we can understand them in terms of sets of quantum numbers that have the characteristic that you can either occupy this box for the quantum number 0 or 1 time, and therefore just this is enough to always get a Gibbs free energy of a form like this.
So absolute, is it always defined as rho whole divided by rho and 3 over?
Yeah. If you want, so this makes the epsilon, if you want, maximally similar to what you would have for a free fermion gas, because if you think of the occupation of your quantum numbers, you see, you would at finite temperatures have some activated processes in there that would populate the whole state. So if you have a ground state of a fermionic system, what you do is that you fill all negative energy modes. Okay, so if the energy is negative, then rho is going to be filled and rho whole is going to be 0. Okay? But if the energy is positive, on the contrary, the holes are going to be unoccupied at 0 temperature. Okay, so that's why if you just rewrite the epsilon is T log of rho whole over rho as rho whole over rho is equal to E to the epsilon over T. Right? Then you see immediately the analogy with a free Fermi gas. It's like thermal activation. Okay? So here it's particularly simple for the Lieb-Liniger gas because there is only one type of particle. We only have, atoms in there. In the case of spin chains, it's much more complicated because there are many different types of particles in there. Okay? So, essentially, if you now have this, you can solve for the thermodynamics of the gas. So, for example, you can. I think yesterday I might have shown you very quickly some plots of dispersion relations, but here we can talk about the densities of the ground state. Sorry, not the ground state, but the thermal state. So, for example, the curves that you have here are curves for the function rho of lambda at different temperatures. So if the temperature is 0, rho of lambda is non-zero only within a finite interval, and then drops to 0. And then if you crank up the temperature, these wings start being populated. Okay? And conversely, on the right, you have the population of holes. It's just rho whole as a function of temperature for a given interaction. Okay? And these plots are, of course, the result of numerical computations of these equations, because this yang-yang equation, again, cannot be solved in closed form, except in the limits of c going to infinity or c going asymptotically close to 0. Okay, but some of these calculations are given for you in the notes if you're interested in looking at that. Okay, so this essentially completes the calculation of equilibrium thermodynamic properties of the Bose gas. Of course, there are many, many things that you can do with these things, and I invite you to just look at the notes for calculations of physical properties like, compressibility and things like that. It's all done in the notes. Okay? So, any questions before I move on to spin chains? Because we have only 20 minutes. Yes?
A question about the formula of, for the limit of Cauchy-Cannon.
Yes.
It seems that there should be a delta function in this limit.
That's correct.
And you're right that this simply is error.
Yeah, so if you go to the notes in section 5.1.3, you will see what actually happens when c goes to 0. So indeed, if you go back to the yang-yang equation, then this Cauchy kernel simply becomes a delta function, okay? So you can perform the convolution straight and then just reorganize terms. And then magically what happens is that the log of 1 plus e to the minus epsilon becomes log of 1 divided by 1 minus e to the minus epsilon, okay? Which is just then the bosonic form It's the form you would have for free bosons with the dispersion epsilon of lambda, because then with your free boson you could occupy the modes by 0, 1, 2, 3, up to infinity. But then of course you would need to resum the series, and that would give you log of 1 minus e to the minus epsilon with an extra minus sign in front of the whole thing. Okay, but this is done for you in section 5.1.3 of the notes. Okay, so indeed things simplify considerably. We fall back onto the case of free bosons when C goes to 0, as expected. And of course, when C goes to infinity, this is particularly simple because the Cauchy kernel just vanishes. There's no equation to solve. Epsilon is just lambda squared minus mu. And then you just get a gas of like free fermions. Of course, these are not free fermions. These are infinitely repulsive bosons. But the energies, the energy levels, are in complete correspondence with a gas of free fermions. Okay, so it's called the Tonks-Giraldo limit. Essentially, the wave functions of the interacting bosons in the limit C goes to infinity are simply the absolute values of the many-body wave functions of a gas of free fermions. Okay, so this is really stuff that goes back all the way to the 1930s. Okay? 17 minutes for spin chains. Okay, so let's do that. Okay, anyway, I invite you to look at the notes. In chapter 6, for example, there are more detailed calculations of physical properties, including the actual equations for excitations, and then finite size corrections, and things like that. Of course, this is interesting if you're interested in doing, for example, a conformal limit of this. You would want to calculate essentially finite size corrections to the energy. You would like to characterize some effective Fermi velocity in there. It's all done for you in chapter 6. Okay, but this I will let you study in your time. Okay, so the nice thing about studying integrable models is that you learn a few monkey tricks that are then more or less directly translatable to other models. That is, if you look at the beta ansatz for the spin chain and already know the beta ansatz for the Lieb-Liniger, you're already part of the way there. So I will just very briefly highlight for you the important aspects of beta ansatz for spin half chains. Okay? And just point out some of the important differences in there that actually lead to some very interesting physics. Okay, so spin half chains. Okay, I call them very often like Heisenberg XXZ. And strictly speaking, the Heisenberg model is only the model with isotropic exchange, but you could call the more general one the Heisenberg-Hochbach or something. But the Hamiltonian that we'll consider is just the XXZ Hamiltonian. Okay, so what we have is a certain exchange constant J that characterizes the strength of antiferro or ferromagnetism here. We have a set of sides that goes from 1 to n, and then on each side, of course, we have these spin half operators. The Hamiltonian that I have, I'll immediately write in the convenient form of so this is just the xy term, right? And then we will introduce a parameter, delta, which is called the anisotropy, characterizing the strength of the exchange in one of the three directions. Okay, so this is the microscopic Hamiltonian. For simplicity, I will just use periodic boundary conditions. So the spin on site n+1 is just the spin on site 1.
Can I ask you one historical question?
Yes.
Do you happen to know, was it really Heisenberg who wrote down this Hamiltonian for the first time?
Yes, yes.
I once wrote a review on this, and then I wrote this, and then the referee said, no, it was not Heisenberg, but then he never told me.
Yeah, so actually it's a bit of a funny history, because if you go back to the original literature, all the papers carry the same title, first of all. They're all sur théorie des ferromagnétismes, or something. And then you have many, many authors doing exactly the same thing. Now, I've always believed that Heisenberg was the first one to actually write down the many-body version of the S.S. That is, so the important aspects of the Heisenberg model are that your spins are coupled with just the full dot product between the two. and that it's a many-body system. So you're not just looking, say, at atomic levels and then couplings between two spins. You're really looking at a many-body thing. So whether somebody before Heisenberg wrote a many-body Hamiltonian with these exchanges, I doubt. But if you say a referee kind of point this out.
Do you know the reference? I mean, I never found this paper.
I can give it to you, actually. I have it here. Yeah, no, I have the whole collection of papers. Actually, yeah, so there's an interesting history behind this as well, because essentially there were attempts at solving the Heisenberg model before Bethe. Actually, Felix Bloch wrote a paper immediately after Heisenberg where he essentially wrote down a beta ansatz. But of course, so we've seen that beta ansatz is characterized by sums of free waves joined together by these non-trivial phases. And what Bloch did is that, he probably was grumpy that morning. He said, I don't feel like dealing with phases, so I'm just going to put all phases to 0 and see where I get. And essentially what happened is that he got too many wave functions. So of course his wave functions weren't exact, and he got the counting wrong. So he got too many states. And that is the point of Hans Bethe, his paper in 1931. He very, very carefully takes the time to deal with the phases and to show that he constructs the correct number of eigenstates. It is absolutely incredible to see to what depths Bethe went in his original paper and the results of his original paper. So he shows that you indeed reconstruct 2 to the n wave functions under very mild assumptions, right? And he talks about string states, he talks about deviated string states, all this junk, and this is totally forgotten until the early 1990s. There are many, many papers in the literature that appeared from the 1990s onwards that are unaware of the fact that Bethe himself wrote equations for these string deviations and stuff. Okay, so Bethe was really, call it 60, 70 years ahead of even things. Yeah, so it's an interesting history. But that would have been interesting, you see, because had Bloch been a bit more enterprising, we would not be talking about the beta ansatz. We would be talking about the Bloch ansatz. Just, so that's the lesson for you young people. If you don't feel like calculating a phase one morning in your life, you might just miss out on something big. So it's the way it goes. But anyway, so historical anecdotes closed. Okay, so let's just be extremely brief on this in view of the time. The coordinate beta ansatz for the spin chain is very, very similar to what we've done with the Lineker. In fact, here you just have the same form of the wave function. So let me maybe even in view, let's see in view of the time, I will actually just point to you the important equations in the notes directly, because it's useless for me to just rewrite everything losing time. So let's just see. So this is all, should we come further? Yes. Okay, so the many-body wave functions are just constructed by taking a reference state, which is a simple eigenstate. In the case of the XXZ Hamiltonian, the simple eigenstate that you can think of is the state where, say, all the spins are up. Okay, this is obviously an eigenstate because the xy term just goes to nothing on there, because the xy term would only move a downspin around. So the reference state, fully polarized spin up, is a good starting point. Start with that. And then you create many body states here by downturning spins in various places. So at a fixed magnetization, and the XXZ Hamiltonian preserves total Z component of magnetization, therefore the number of downspins is a constant of motion. Therefore each eigenstate is representable in terms of the positions of the downspins in the block of n spins. Okay, so in such a fixed magnetization sector, the beta ansatz is just a collection of free waves of the positions of the downspins. okay, for the region where magnetization is greater than or equal to 0. If you're below 0, you just do the construction from the fully downspin. Okay, so maybe it's a bit difficult to read. We'll see. So that's of that form, right? So again, the one downspin eigenstates are completely trivial. The energy is now cosine of k because you have a lattice. Okay, so in the presence of a lattice, there is bound curvature. Instead of having free dispersion k squared, you will now just have cosine k. And then the many body case of this takes again the form of the beta ansatz. Okay, so again, free waves combined together with different relative amplitudes associated to two-body scattering phase shifts. Now, the two-body scattering phase shifts in the case of xxz are very complex functions of the internal momenta of the particle. So this is this function here. You see, if you have two excitations with momentum k1 and k2, contrary to what happens in the Lieb-Liniger gas, the scattering phase shift depends not only on the difference of momentum, but also on the total momentum of the block of two spins scattering. Okay, this is completely expected because we're on the lattice once again, right? So because of band curvature, there is no notion of any residual Galilean-like invariance that allows us to simplify the thing. So, if for example you have two downspins bound together in a certain state, the state might be bound if it's at low momentum, but if you give it much higher momentum, it might unbind. Okay, so if you want the difference between the physics of the xxz chain and the Lieb-Liniger model, is that here, in xxz, we essentially immediately obtain the possibility of having a whole periodic table of possible fundamental particles, depending on the state of bindedness that we can have between our downspins. These downspins, they're magnons. Okay? The terminology is magnons. You have a single dispersing downspin, you call it a magnon, and then essentially the beta ansatz is just a combination of many, many magnons together to form the eigenstate. Okay, so that's the difference here. So you have this non-trivial scattering phase shift here between excitations. Nonetheless, the many-body form of the beta ansatz, I don't know if I can... so the many-body form of the wave function that you have here is completely analogous to the wave function that you had for the Bose gas. It has textually the same form. Okay, same summation over permutations of the distribution of the quasi-momenta onto the particles. Okay? Now, of course, it gets more complicated for the spin chains because the physics of it depends very, very much on the value of anisotropy. So in the notes, what I've included for you this time is just the specialization to the isotropic point, which is in the sense the most instructive. It's also the most important physically, because in nature, essentially nature likes XXX above XXZ. Okay, so there are many, many more experimental realizations. I'll show you many, many experimental realizations of the isotropic antiferromagnet. So that's the one that you have in the notes. So in that case, what you do is that you parametrize the momenta in terms of rapidity. So in the case of the Bose gas, we had lambda, which was just directly like a quasi-momentum. Here, the rapidity is defined with a non-trivial relationship to the quasi-momentum of the particle. And this relationship here is just this one for the case of the isotropic antiferromagnet. Okay, so one important aspect of this is that if you look at the possible values that the momentum can take on the lattice, it's very different from Lieb-Liniger, right? So in Lieb-Liniger, we've got a continuum model, no ultraviolet cutoff. The momentum can go from minus infinity to plus infinity. For xxx, of course, for xxz, we're on a lattice, therefore there's a momentum limitation, there's a Brillouin zone. The Brillouin zone has a width of 2 pi. There is no physical difference between momentum k and momentum k plus 2 pi times an integer. Okay, so the quasi-momentum with this parameterization here, if I choose my lambda to be real, spans the whole, say, first Brillouin zone. Okay, and in that case, the nice thing is that the scattering phase shift here now depends only on the difference between these rapidities. Okay? And once again, if you take the beta wave function and you impose periodic boundary conditions in the positions of all the rapidities, then you get quantization conditions. These quantization conditions are the beta equations, and for the XXX model, they take the particularly simple form of equation 8.3. Okay? So this is essentially the equivalent of the equations that we wrote for Lieb-Liniger. I remind you that in the case of Lieb-Liniger, on the left-hand side, we had e to the I lambda j times L. Okay? Here it's just different. Just like the kinematics of the spin chain is very, very different. Okay? So these are the beta equations, and now once again you can go to a logarithmic form. I can move this. So you can go to a logarithmic form of these equations, which is given here. Okay, so once again there's the first term on the left, which is just the free kinematic term, and then there's the interaction term, and then the introduction of the quantum numbers for the labeling of our states. Okay? Now, there's an extremely important difference between the two models, and this is, well, so first of all, the theta 1 is a different function, but that's not so important. What's much more important is the sign before the second term. Okay, now it's a negative sign. Essentially, what it means is that, unlike with the Bose gas, the beta equations now support solutions taking the form of rapidities moving in the complex plane. Rapidities are not confined to the real line. You can have eigenstates here where, say, you have two rapidities conjoined together in a so-called string. Okay, so I kind of give you indications of that in the notes. So you see, let me just again.
What do you mean by a complex?
So I mean that there would be eigenstates. So I would solve equations 8.4 for lambdas. Okay, and then depending on the eigenstate, I would sometimes have eigenstates where some of the lambdas are complex. Yeah, so what does it mean physically? Essentially what happens is that the complex momenta, they appear in well-defined structures. And these well-defined structures always take the form of a kind of ladder of rapidities that all have the same projection onto the real axis and that have a well-defined, if you want, ladder spacing between rapidities. Okay, so you see it from the beta equations here. If you reflect hard enough on these equations here, you will see that if there is a complex rapidity with a positive imaginary part, there has to be another rapidity with the same imaginary part, but one step below. Conversely, if you've got a rapidity with a negative imaginary part, it has to be accompanied by another rapidity with an imaginary part, which is one step above, 1 unit above. So then the stable structures are 2 strings, 3 strings, 4 strings, 5 strings, etc. Up to whatever you can have with XXX, all are possible. Now what does it mean to have a complex lambda? If you have a complex lambda, you have a complex k. Okay? If you have a complex k, e to the I kj becomes e to the minus some number. So it means essentially that 2 downspins become exponentially confined to each other. Okay, so it means that there are excitations in spin chains that correspond to free scattering single downspins. Yes. Okay, so a 2 string is essentially 2 downspins that can form like a breathing mode, but they're always exponentially close to each other. So you can construct them on one end of the chain, throw them in, and they will just keep on doing this irrespective of what they encounter. Even if they collide with other downspins or with other structures, they will emerge out of that as precisely the same bound state. Okay? But that's a sign of the richness of the physics of the Heisenberg model, and also quite generally of XXZ, because these bound states can appear. And of course the wave functions are utterly different. because bound states really you see in scattering experiments and whatnot. Okay, so they're very, very important. So, you know, that's one of the things. So now essentially in a 10-second summary, in the notes, what you have is just the construction of the possible sets of states of XXX. Which ones can they be? And then the excitations, and then the finite temperature thermodynamics. So this afternoon, maybe I'll take a quarter of an hour to run you through the most important aspects of the physics of XXX, and then I'll move on to the algebraic beta ansatz. And in the fourth session, once again, I will really talk much more about the physics of these models. Okay, but I will use the language of the ground state, excitations, etc., that we've been developing. Okay.